The next section is shared ownership and reference counting. So far we've looked at transferring ownership. We've looked at threads in Rust and scope threads, so we just finished that. When sharing data between two threads where neither thread is guaranteed to outlive the other, neither of them can be the owner of that data. So what you need is for the data shared between them to live as long as the longest living thread. And so that's where it gets into statics, which is the first of the ways to create something that is not owned by a single thread. So you have something that lives forever, essentially. So the simplest one is a static value, which is owned, quote unquote, air quotes, by the entire program instead of an individual thread. So it goes beyond all these threads and lifetimes. In the following example, both threads can access X, but neither of them owns it. So we can set up a static here. It's all right, where's VS Code? Okay, so we're starting with static X. Just move my mouse out of the way. Static X, and this is a what is it? 1, 2, 3. And then we do we spawn 3 threads, or 2 threads, I mean. Thread spawn, and we don't do that, we do that, and thread spawn. And we're going to debug, use the debug macro on them. And X, like that. There we go, reference to X. I'm typing slow today. Okay, there we go. Now when we do this, you can see it kind of stops right away because it doesn't join to stop the threads before main finishes, so we'll just do that. So join unwrap, and then do it again, and then you can see it's going to print them out. There you go. So X is 1, 2, 3, 1, 2, 3, and so it's a static and it lives forever essentially. And we have it inside main here, but you can of course you can do it outside, and that's what you'll usually do with a static. But yeah, you can stick a static or a const inside. It doesn't always have to be outside of main. There's no rule for that. So there we go. Back to the book. So a static item has a constant initializer. It's never dropped and already exists before the main function. That's where we moved it out of the main. Every thread can borrow it since it's guaranteed to always exist, so no lifetime issues. Now this is the next one is the interesting part, leaking. You can make something static like out of nothing. So another way to share ownership is by leaking an allocation. So you use box leak, and you can release ownership of a box, and you promise to never drop it. So a box will, it'll drop when it's out of scope, but if you leak it, then it'll be around forever. From that point on, the box will live forever without an owner, allowing it to be borrowed by any thread for as long as the program runs. And so you can see what you do is you make a box, and then you leak the box, and you can do it all on the same line. So let's do that. All right, back to main. Delete all of that. Okay, so we will start with X. What are we doing? Static I32 3, and what we do equals box leak. And to leak a box, we have to have a box, and to make a box, you do box new, and then inside that you stick in the 1, 2, and 3, and now you have yourself a static created out of nowhere. And then you can do the same thing, thread spawn. We're doing debug X, and thread spawn debug X, like that. Oh, I forgot to move it. There we go. So removing and the book actually talks about this. So first I'll just do move, and you can see the compiler is telling us to do it too. Let's see, cargo run that. And it's going to do the same thing as before, where it tries to print it, but we didn't join it. And we could join it, but it's pretty obvious that it's going to print 1, 2, and 3. So not going to bother to do that. And then the book notes, so the move closure might make it look like we're moving ownership to the threads, but a closer look at the type of X reveals that we're only giving the threads a reference to the data. So you're just moving the reference in. And a little note here, references are copy, meaning that when you quote unquote move them, the original still exists, just like with an integer or boolean, all those primitive types. And this is also important point. Note how the static lifetime doesn't mean that the value has lived since the start of the program, which makes sense because we did this after the start of the program, but only that it lives to the end of the program. So the past is simply not relevant. So you can have a static that starts before main, and it goes from before the program right to the end, or you can make it inside with these tricks like leak. And then, why don't you just leak everything? Because this is really convenient, and it's, well, here's the answer. The downside of leaking a box is that we're leaking memory. It's not unsafe, but you are leaking memory. So you allocate something, but you never drop and deallocate it. So it just sits around forever and never gets cleaned up. And this can be fine if it only happens a limited number of times. But if you keep doing this, the program will slowly run out of memory. So you don't just want to go around and leak stuff forever. And I also had an interesting example of leak. So struct has stir. Let's say for some reason you have a this thing, some type. There you go, static stir. So it's a static stir, so you don't need to worry about the lifetime of this. It's longer than this has stir, so you don't have to do that. Tick A or whatever. And let's say, for example, I don't know why, but input from string for has stir. And so you have the from function and input string, and then you return a self because that's the type. And then, so let's say data input like that. And so if you do that, it says, expected a stir, found a string. So, you try to give it a ref, but, it's a reference to something that drops later on. So that's not going to work. And so it says it doesn't live long enough. And that's where you can box leak. One of those things you can technically do. You probably don't want to do this. But it's an interesting example that you can just do that. So if you have a string, so now you can say, okay, let my string equals string from I am a string. And then you can say, let my new type equals, what is it called? Has stir from my string. And you can see it builds it, no problem. So it takes the string that was going to be dropped, and then it puts it in a box, and then it leaks the box, and it lives forever. And then there's no problem with this has stir holding a static stir. So you don't have to. Well, I don't know what the actual purpose of that is, but there you go. That's an example of how you can just leak a box. And there we go. And so tomorrow we'll, let's see, it moves on to reference counting. Maybe I should, I'll just go on. Still got some time. Okay, let's go to reference counting. To make sure that shared data gets dropped and deallocated, we can't completely give up its ownership. Instead, we can share ownership. By keeping track of the number of owners, we can make sure the value is dropped only when there are no owners left. And so, yeah, RC goes... it starts with one owner, and then if you do RC clone, then it goes to 2, and so on. It keeps track of who's owning it. The Rust standard library provides this functionality through the standard RC type, short for reference counted. This is funny. Everybody calls it reference counter, but technically, if you look at the documentation, it says reference counted. It is very similar to a box, except cloning it will not allocate anything new. It just increments a counter stored. So 1 to 2 to 3, and so on. And if it drops, it goes back to 1 and eventually 0. Both the original and cloned RC will refer to the same allocation. They share ownership, and there's this, this is interesting, the assert equal. So it shows that it's the same allocation. So let's do that. All right. Let's delete my stuff. Where's my, get rid of that. Okay, so let A equals RC new, and what are we putting in? A 1, 2, 3, of course, and then we're going to say let B equals A dot clone, like that, and you can see it. There's the type there. Sometimes you'll also see RC clone like that. So either way, same thing. A dot clone, and then what are we doing? Assert eq. Actually, instead of assert eq, I want to see if we can print it out. Let pointer1 equals A dot as pointer, and same for pointer2 equals B as pointer, and then I'll do assert eq. Pointer1, pointer2. Let's see if we can print it out. Pointers. Pointer1. Do we have debug print? There we go. Pointer2. Like that. Probably can't see that, so I'll move it up. There you go, pointer, there's the first one and there's the second one. And of course it we did an assert eq and it did not panic, so that's another way of proving that they're the same allocation. Okay, back to the book. Dropping, there we go. Dropping an RC will decrement, so reduce the counter by 1. Every time. Only the last RC, which will see the counter drop to 0, will be the one dropping and deallocating the contained data. However, an RC is not thread safe, so if we were trying to send an RC to another thread, we would run into the following compile error. And we probably don't need to type this. This is pretty obvious. So if you do thread spawn move, it's going to give you this message: RC cannot be sent between threads safely. As it turns out, it is not thread safe. The reason why is because if multiple threads had an RC to the same allocation, they might try to modify it at the same time, and that's not okay. So what you need is an atomic type, which is ARC, atomically reference counted, or as people always say, atomic reference counter. You'll hear that mostly, I think. But here's the official name. It's identical to RC, except it guarantees that modifications are indivisible atomic operations. And that's what atomic means, indivisible. So it's not, it can't be further divided. Like there's nothing getting in there. If you have an atomic operation, it's only one can go on at the same time. And that is why it is safe to use with multiple threads. And we have this example here, and it's also basically the same as before, except you have a thread spawn and you're not getting any compile errors anymore. Let's see. So we put in an array, starts at 1, cloning it. Actually, let's print that out, because you can print out the number of. You go dot strong, I think it was, because they're strong. What are they called? Strong count. There's like strong and there's weak, but the book will get into that in a second, or maybe in a chapter or two. Okay, so we're going to go arc new, 1, 2, 3. Just to make sure I'm showing you VS Code. Okay, and then we're going to make B, which is a clone. Oops, I did that again. A clone of that. And then we're going to do thread spawn, and we're going to be totally okay using the move keyword. And then we can debug A, use the debug macro, see what it looks like. Same for B, we can debug them both. Then run that. And then of course, if you do join unwrap, it'll actually print it out before the main function ends. Oh yeah, I wanted to, that's right. So print out, let's see, number of references. There you go, A dot, let's see, what was it? Was it count or was it strong? I always forget. A dot, or was it strong count? I'm going to find it. Oh, that's right. Arc dot, strong count. There we go. All right. So you can see number of references equals 2. And then if you clone this again, let's see equals A dot clone, then it's going to go up to 3. There you go. So it's got three owners. All right, back to the book, I think. Let's see, both threads get their own arc, blah, blah, blah. We did that. Yes, we did that already. Naming clones. This is just a little interesting thing. This is just about like making your code readable. So having to give every clone of an arc a different name. So we called it A and B and C. Yeah, that can be annoying. So every clone is a separate object, but it represents the same value. And so naming them differently kind of feels weird to a human reader for sure. So Rust allows and encourages you to shadow variables. And the way you do that is you just give it the same name. And if you do that in the same scope, the original variable cannot be used anymore. However, we're doing it inside. So we have these new threads here. Hold on a second, but by opening a new scope, that's right, a statement like let A equals A dot clone, so it's the same name here, can be used to reuse the same name within that scope, but the original variable is, it's available outside. So you can see inside here, A is, A starts here, and then later on it debugs A, and it's just, it's hanging out on its own here, but inside this scope here, you just say A equals A dot clone, and that feels right because it's the same same allocation anyway so to us it feels like, you know, A should refer to A, and if you look at this you can see, okay, you've got this this A inside here, and it's referring to the same data here, so to us it's quite readable. By wrapping a closure in a new scope, we can clone them before moving into the closure without having to rename them. Yeah, so you've got A here, B here, and then you spawn the thread. So the better way to do it is to spawn the thread, clone it, give it the same name, and then you can do this move, and then you have the same name, and humans find that readable. Last part, because ownership is shared, let's see. All right, they have the same restrictions as shared references. So we have not changed anything. They don't give you mutable access because the value might be borrowed by other code at the same time. And so if inside this example, if we tried to do this a.sort. That would mutate the data, and you're not allowed to do that. And of course, later on, it gets into mutex and rwlock and so on, and that's what lets you mutate it. But with an arc alone, you can't mutate the data. So there we go. I think that's enough for today. And tomorrow's going to start at borrowing and data races.